let's begin off with recalling the definition of a limit. Okay, so the definition for the statement lim x approaching a f of x equals L, okay, verbally means that this is the limit of f of x, okay, limit of f of x as x approaches a equals L. Okay, so another way of saying it is as x approaches to a, f of x approaches to L. In other words, what is the value of f of x near a, rather than saying what is the value of f of x at a. Okay, so this is a definition of limit. And let's just come to an example here. So let's consider we want to find the limit for a parabola. Okay, so the function that we want to deal with at this problem is negative x plus 1 and then x minus 3. Okay, so do you recall how to draw this parabola? Well, it's an upside down parabola. It's an upside down parabola crossing the x-axis at the 2 points negative 1 and positive 3. Okay, so those are the two zeros of the parabola, and we have a parabola that's open downward. Okay, so let's say we want to find out what is the limit x approaches to 2 of f of x. Okay, what does this equal? And let's see how we can evaluate this. Okay, so where is it graphically when x equals to 2? Well, 2 is over here. So we're dealing with the vicinity of f of x at that at around that those places. So as you recall, one way of evaluating the limit, though it's not the best way, and it's a graphical way and it's an approximate method, is to use the same technique we did for the problem of tangents. Okay, so we need to evaluate f of x when x is some number greater than 2, and then let it come closer and closer to 2. And we do the same thing as x is some number closer to but less than 2, and then we let it get bigger and bigger as we get to 2. Okay, so let's just go to the next page here. Right, so some number greater than 2 is 2.01. So let's find f of x. Well, let's find f, evaluate at 2.01. So substitute our x value with 2.01, 2.01 squared. Oh, by the way, I forgot to mention. Okay, so let's first just expand our f of x. Okay. Expanding this gives us x squared in the middle minus 2x minus 3. Okay. So this comes out to negative x squared plus 2x plus 3. The reason I expand this is so that we can do the evaluation easier, and that actually I'm going to break this function up into its 3 terms and then show you what the value of limit are for each of them. Okay, so with this expanded, let's find f evaluated at 2.01. And the evaluation means we replace x with that particular number. So everywhere we see x, we replace it with 2.01. Okay. So this, if you just crunch it out on the calculator or work it out on the side, you will get these numbers, which equals to 2.9799. Okay, which you can see is very close to 3, but it's actually a slightly less than 3. Okay, let's do the same thing from the left side. Okay, so from the left side, let's say we want to find the f value at 1.99. So this, if we replace all our x with 1.99, okay, you can work this out and you will get a value of 3.0199, which is about 3 and is slightly greater than 3. Okay, so what's going on here on the graph? Well, if we zoom in at 2, okay, remember our parabola that looks something like this. Here's 2. at 2.01, let's just say this part is 2.01. Okay, and let's just say the upper part there is 1.99. And you can see that the y value here is 2.9799, and the y value here is 3.0199. Okay, which kind of hints to us that if we were to find the y value, or not just the y value, the limit at x approaching to 2, then the y or the f out value should approach the value 3. Okay, so if we were to now evaluate f at 2, okay, this gives us negative 2 squared plus 2 times 2 plus 3, which gives us the value 3. Okay, so in this case here, you can see that our values, as you have our limit as x approaches to 2 from the right. Okay, remember, from the right is this way. So approaching from the right, the y value gets closer and closer to 3 from below. And approaching x from to 2 from the right, left, okay, then our limit gets closer and closer to 3 from above. Okay. Now, I brought out the evaluation when x equals to 2 just to show some, just to give us that sanity check in a way. Okay. But I'm going to get back to this value. Okay. So let's break up our term. Let me just, oops. Okay, let me highlight this in red now. So let's break up our f of x into 3 terms. 1 term, 2 term, and 3 term. And let's deal with this constant term first, then the linear term, and then the quadratic term. Okay. So let's see what's going on if we were to evaluate the limit at those 3 terms. Alright, for the first part, let's say now we have a function g of x equals to 3. Okay. Alright, so what I'm doing here is breaking up f of x into 3 terms, and then find the limit as x approaches to 2 for each of those 3 terms. Alright, so let's recall what the function g of x equals to 3 would look like. Okay, so equaling 3 just implies a straight flat line, okay, horizontally going across 3. So when we say the limit x approaches to 2 of our value 3, okay, the limit in this case, you can see it's clearly 3, because as your x approaches to 2, whether it's from the left or whether it's from the right, okay, all the values are just 3, and so it's a good guess in a way. And I emphasize the word guess. It's a good guess that what happens at the 2, right? Around 2, the limit value is always around 3. Okay, so let me just draw this clearly here, right? What we're doing in evaluation limit is, imagine putting a little circle at the destination point, all right, and anywhere close to the circle are those x values that you evaluate for the f of x that those are the limit values we're trying to find. So earlier, this is 2.01, this is 1.99. Then you can see the y corresponding y values will approach that limit value we want. And in this case, it's 3 everywhere, okay, within the circle. So for that reason, limit as x approaches to 2 for our expression 3 is equal to 3. Okay, so this is our first term that we evaluated. Next, let's consider the second term, the linear term, which is 2x. Now, graphically, we have 2x represented by a straight line. So at 2, well, you guessed it, this is the value 4. But we cannot just say that the limit at 2 equals to 4 without doing some showing. Okay. Imagine us approaching to 2 from the right. If we evaluate g of x as x approaches to 2 from the right, then you can see the corresponding y values will get closer and closer to 4 from above. Okay, and likewise, if we approach 2 from the left, okay, then the corresponding y values approaches 4 from below. So in this case, the limit x approaches to 2 for our expression 2x is equal to 4. Okay, all right. For the first case, it's because as x approaches to 2, right, our constant 3 approaches to 3. It's a constant, it doesn't change. Now in our second case, it's not just a constant, it's a linear variation. So as x approaches to 2, 2x approaches to 4. Okay, so we have two of our terms now. So let's now come to the third term, which is the x squared term. Right, and we'll do something very similar. So g of x equals to x squared. So for now x squared, we have a parabola that opens upward. Okay, and notice that these three curves are all continuous, meaning that I did not raise up my my pen as I drew those curves. Okay, so likewise with this parabola, there are no holes anywhere along the curve. Now because as x approaches to 2, our x squared approaches to 4. Okay, and again you would consider approaching it from the right and approaching from the left. The limit around this circle here, right? These numbers that we're dealing with. Okay, right. So there's these y value numbers. They are all getting near the value 4. Okay, so for this reason, we say our limit x approaches to 2 for x squared is equal to 4. Okay. How do I know these are the limits? For the first term 3, the second term 4, and the third term 4? Well, I see it on the graph, right? The value here is around 3, the value here is around 4, and the value for the third term is around 4. Okay, so bring all these three together. Our limit x approaches to 2. For the first term, we have 3. For the second term, we have 4. And for the third term, we have 4 as well. Now for the third term, we have a negative. So let's just put a negative here. So if you have a negative, then you just have a multiply with the negative. Okay, so adding all these three limits up, negative x squared plus 2x plus 3, okay, just means we have the limit x approaches to 2 for the first quadratic term plus limit x approaches to 2 for the linear term plus limit x approaches to 2 for the constant term gives us negative 4 plus 4 plus 3, and this evaluates to 3. Okay, so this is a very basic way of evaluating limits, and of course you can see it's not a precise way nor a rigorous way just yet. And actually, now coming back to what I was saying earlier, well, why don't we just evaluate f at 2? I mean, that would also give us the value 3, wouldn't it? Indeed, it does. And in fact, you recall this gives us the number, the evaluation equals to 3. So we have the same value as if we approach x approaching to 2, the limit equals to 3, versus evaluating the function at 2, giving us an evaluation of 3. But we cannot do this. We cannot just evaluate x at 2 and then find the value at 3. Find the y value to be 3 and then say that is the limit. The reason is because that's not how the definition of limit is. The definition of limit is as x approaches to 2, f of x approaches to 3. Right? So there is this matter of arrow. It's very important. Okay, and I'll highlight this in the next example. Okay, suppose now, what if we have a function f of x that is defined as following? Suppose f of x is now broken into two components, okay, or two parts. The first part being what we had earlier, okay, negative x squared plus 2x plus 3, but this only applies when x is not 2, and f of x is equal to 1 when x is 2. Okay, so what's going on here? Well, graphically speaking, okay, again, we can consider the two zeros to help us graph the parabola. Okay, graphically speaking, what happens is our parabola looks exactly the same everywhere else except when x equals to 2. At x equals to 2, we have an open circle. We have an open circle because of this first component of f of x, saying that our f of x has the shape of a parabola at everywhere except x equals to 2. And at x equals to 2, our f of x is just that y value equaling 1. So x equals to 2, we have a solid circle at the value 1. So now, if we were to evaluate f of 2, right, first, let's say evaluating f at 3, then what you do is replace x to be 2, or to be 3, everywhere we see x, and this would get us some number for sure. And you can calculate that. And the reason why we use this part, or the first component of this piecewise function, is because x is 3, x is not 2, so we used this component. Okay, but what happens when x is 2? If x is 2, then we have to use this piece. That's how you would interpret a piecewise function, and how you would go about evaluating a piecewise function. So when x equals to 2, f of 2 equals to 1. And we see that on the graph. X at 2 gives us a f value of 1. Now compare this with our limit. The limit x approaching to 2 of f of x. Because x is approaching 2 but not at 2, then all of our f of x components, right, then this expression of x, we cannot use the second piece in the function. We cannot use this piece at all. Okay? Again, the reason is because x is approaching to 2, but x is not 2. So if x approaches to 2, then we're dealing with the first component. Okay? We're dealing with this first piece here. Okay, so I keep getting this mixed up. So if that's the case, then our f of x must be replaced by the expression, by the first expression. Okay? And then once we replace f of x with the first expression, then we just go ahead and evaluate the limit for each of the terms as according to how we did before. X squared is a function. It's a continuous parabola. It's the value around 2 for x squared is 4, as we saw earlier. So now the limit of the first term is -4. The limit around 2 for the linear term 2x is also 4. And then for the constant, well, constant is a constant everywhere, regardless where you are for x. That's just equal to 3. So the limit, in this case, is equal to 3. Okay? So notice how f at 2 is 1, but f approaching to 2 is actually 3. Okay? So putting this together, the limit f approaching to 2 for our parabola, in this case, is just f of x, is actually not equal to f at 2. Right? So this came from limit x approaches to 2, x squared plus 2x plus 3 equals to 3. Whereas this one here, f of 2 is just 1 based on definition. Well, so why can't the limit be equal to the evaluation? Well, again, it's because of a gap in our function. Okay, so remember there's a gap at 2, right? Another way of saying the gap is when I draw this parabola, I have to lift up my pencil and skip over this point here and then continue onward. Okay, so there's a gap. So whenever we're evaluating a limit of function, right, we cannot just simply substitute x for our destination point a. Okay, so in general, right, the limit x approaching to a, f of x equals to L. Okay. When we evaluate this limit, we cannot just simply substitute x for a, but rather we can only have x approaching to a. Okay, and when our f of x, our expression of x, gets even more complicated, the work actually becomes more involved, and in fact, it could get quite tedious. Okay, in our example here, what we did is we broke up our expression into 3 terms, and we had to consider each term separately, dealing with the value of f in the vicinity of x equals to 2. And the thing is, for each of those 3 components, we could clearly see on the graph that what those limits are. Right? But it doesn't always work nicely for us. So when we come to evaluating limits, it could get very, very tedious if we always approach this using a graphical argument. Okay, so what we need to do in our next video is we must establish, okay, some rules or some laws of limits. And by knowing these laws, okay, we can then go ahead and evaluate limits in a very rigorous way and yet fast way. And whatever we would get, these will be precise answers. So this next video will help us get the mechanics of evaluating limits.